Hello, this is Dr. Arberg, and welcome back to our course, Introduction to Reinforcement Learning Motion Control. We are in lecture 11. We'll discuss neural network optimization using Bellman equation and linear programming. The optimization methods that are available in reinforcement learning are linear programming, and this is to find a maximum of a linear system, and then nonlinear programming to find maximum global of a nonlinear system. It could be also the negative, which is a minimum in both cases. And we have here an article that discuss dynamic programming versus linear programming applications for a certain problem. The functions that we try to optimize, for example, when we minimize, could be with one minimum or could be with several minimums, or the negative could be maximum. Both of them is a problem of optimization. When we linearize the space and the function, we get into a linear function, and there where we use linear programming to find the point of minimum. And we use dynamic programming for a nonlinear function. Now, the dynamic programming perspective of reinforcement learning optimization is shown over here. This is about the only equation that we take a look at, but I think it's interesting because it is very closely related to what we discussed so far. So let's try to make sense out of it. We said before, as we saw over here, that the convergence, the optimum solution, is when the expected value of the total reward for the entire process by the critic equals to the total reward as calculated by the actor. So what we see over here is this is the equation of total reward on the left-hand side and on the right-hand side. On the left-hand side, we have the critic estimate of the total reward. This is the green function. And on the right-hand side, we have the reward of the actor that we just got out of this iteration, plus the future reward, which will come in after the iteration which is completed. And there is a hyperparameter, which is called the discount factor, which can actually diminish a little bit of its value. So both of them are the total reward estimates. We have over here the blue on the right-hand side by the actor and the green on the left-hand side. Now, the temporal difference is actually the difference between the two. If we take the difference between these two lines, this is the difference. And we like to minimize this difference in order for the two to converge. So this is minimized here by dynamic programming. It can also be minimized by linear programming. Now, this particular equation right here is a very important equation, and it is called the Bellman optimally equation. Very, very basic in reinforcement learning. And again, here's what we see. The left-hand side, what the critic is giving us, and over here, the right-hand side with the discount factor, we get the actual reward plus the future reward. And this is the expected of all of them in the future. So this is the so-called Bellman equation. But the question is now, should we use linear or dynamic programming in reinforcement learning? And here's an article that states that using linear programming to boost your reinforcement learning algorithm is not a bad idea at all. But the answer to this question is, of course, by the AI machine learning experts. That will be the job for this specialist to make that decision. With that, I'd like to thank you for listening, and I look forward to talk to you in our next lesson. Thank you.